Okay, this was the general introduction of per unit system, when we did not call it apply it to a particular equipment. We did not solve the system specifically for any transmission line or generator or any parameter. Now let's see the per unit system when we particularly apply it to transformer. So this is just one practice. Once you solve it for the transformer, the same kind of formulas and same pattern will be equally applicable to the whole power system, whatever the equipment is involved in the power system, whether we solve it for the generation part or we go towards the transmission part of the transformer. We will have the same approach that will be applied for the complete calculation of per unit system. Well, if you recall the transformer, I hope you are familiar with this. Now, a transformer is just used to step up or step down the voltages and currents in a power system as the requirement may be. We require a step up transformer or we require a step down transformer, so we do this transformation. But in this case, the total power transmitted, however, it remains unchanged if the losses are neglected. But it's quite obvious that the voltage and current parameters are different on both sides of the transformer. Voltage will be different, current will be different, but the power on both sides will be equal. And the same kVA rating applied to both the transformer windings. And if the primary and secondary parameters are indicated by the suffixes P and S respectively, then we have the quantities on both sides of the transformer as this is the general formula that is applicable. Vp over Vs is equal to Np over Ns, which is the ratio of turns ratio of primary to turns ratio of secondary, and it is equal to reciprocal to Ip over Is. Vp over Vs is equal to Np over Ns is equal to I think this is not correct, it should be Is over Ip. Currents are inversely related to voltages and turns ratio. So these are general formula that we apply to the transformer. And if impedances are written as primary impedance is equal to Rp plus jXp and secondary impedance is equal to Rs plus jXs for the primary and secondary circuits, then we have to refer these impedances because there is a different circuit on the primary side and then different parameters on the secondary side. So in transformer, it is a normal practice to refer the parameters from primary to secondary side, or we have to refer the parameters from secondary to primary side for simplicity. So for this referring, let ZPRS is the transformer primary impedance referred to secondary, and ZSRP is written as the transformer secondary impedance referred to primary. So in this case, if you write the formula for primary impedance Zp, it is equal to simply the ratio of voltage and current, primary voltage to primary current. So if replace the value of Vp, which is equal to basically Vs times Np over Ns, and Ip is equal to Is times Ns over Np. So here you can see this is equal to Vs over Is times Np over Ns whole square. So Vs over Is is equal to basically Zs, and now it will be equal to basically primary impedance referred to secondary. So if we rearrange these terms, we get Z impedance, primary impedance referred to secondary, equal to Zp times we just have to invert this combination when we take it on the other side of the equation, and this is the equation for the primary impedance referred to secondary. Similarly, we can in the same pattern we can solve it to show that the secondary impedance referred to primary is equal to Np over Ns whole square times Zs. So keep these formulas in mind when we have to calculate the total transformer impedance referred to primary. Then it is equal to basically primary impedance plus the referred secondary impedance, and it is equal to Zp plus the equation that we have solved for the secondary impedance referred to primary. And similarly, for the total transformer impedance referred to secondary, we just have to replace the value of Zs plus primary impedance referred to secondary. So it will be equal to basically Zs plus Zp times Ns over Np whole square. So these are the general formulas when we solve the transformer impedance referred to primary or referred to secondary. This constant need for referring the quantities to one side or the other, it may be avoided by a judicious application of per unit system where the magnitude of these quantities remain unchanged for both sides of the transformer. Yes, it's true, this is another very big application or advantage of per unit system, that this conversion process that we are following by referring to primary, referring to secondary, this system can be ignored. It can be simply overcome by using per unit system, because the per unit system, the magnitude of these quantities remain unchanged whether we solve the system from primary side or we solve the system from the secondary side. Let's see how this system works. Let kVA be the general base kVA, and kVB P and kVBS are the base voltages in primary and secondary circuits. So kVB over kVBS is equal to NP over NS. So basically kilovolt, base value of kilovolt at primary divided by secondary, like we normally write it like Vp over Vs. So it is the base value of primary to secondary is equal to Np over Ns. So in this case, per unit impedance Zs is equal to actual value over base value, and actual value is Zs over Zb. So Zs over, replace the formula for Z base, and it is equal to kV square into 1000 over kVA, and it is equal to Zs is equal to Vs over Is times this formula, rearranged formula. And now replace the value of Vs and Is in this equation, rearranging the terms, and you just have to simplify it. It is equal to Vp over Ip times Ns over Np whole square, and Vp over Ip is equal to Z primary times kVb secondary over kVb primary whole square multiplied by kVa base over kV base whole square times 1000. Well, if you go through this whole derivation, you just get the final answer equals to Z primary per unit value of the Zp. So this whole derivation will prove you that the per unit value of secondary impedance will be equal to the per unit value of the primary impedance. I mean, the same formula you will obtain which is used for the per unit value of the value of primary side. So it's simply say that it doesn't matter whether we use the referred value to primary or we refer the values to secondary side, the per unit value remains the same. So using per unit value will reduce the need of this conversion. So for actual voltages, kilovolt, and for primary and secondary, kVs per unit will be equal to kVs actual value over base value, it is equal to this formula, and kVs per unit is equal to basically kV primary. So the kilovolt values, per unit values of kilovolt will also be remain same on primary and secondary sides, and same is the thing for the currents. So you can go through this derivation to verify the results that the Is per unit is equal to Ip per unit, kVs per unit is equal to kVp per unit. So thus the numerical per unit currents are also independent of the turns ratio terms. This is the second example of transformer in which the per unit system is will be verified. In the given data, a single phase transformer rated 10 MVA 10 kilovolt primary to 1 kilovolt secondary has a total impedance referred to primary as ZTRP is equal to this value. It is supplying a resistive load of 9 ohms at 900 volts across its secondary load terminals, and we have to calculate the per unit value of transformer resistance, reactance, inductance, voltage and current, all the required values. When all the quantities are referred to primary circuit and primary kVA and kV are chosen as base in the first case. In the second case, all the quantities are referred to secondary circuit and secondary kVA and kV will be chosen as base. So you have to solve the system twice, once taking the primary values as base and other on the second circuit taking secondary values as base. So let's see the solution. Calculation for in the first case, and we are using the primary kVA and kilovolt as base values. kVA base will be 10,000 kVA and kV base is equal to 10 kV, which is given of the primary parameters. And in this case, current value will be equal to kVA base over kilovolt base, it is equal to 1000 ampere. Using the formula of Z base, it is equal to kV base whole square into 1000 over kVA base, it is equal to 10 ohms, and transformer impedance referred to primary total impedance is equal to 0.15 plus J15 ohms, it's a given value. Then Vp is equal to Vs times Np over Ns. Just calculate the actual values or all the values that are required before going towards their per unit calculation. And Is is equal to Vs over RL it is equal to 100 amperes. IRP is the actual current referred to primary. So referred to primary using the formula, it is equal to IS times N2 over N1, and it is equal to 10 amperes. Now when we have to calculate all this, convert these parameters into per unit, so just divide their actual values with the base values. So Z per unit is equal to ZA over ZB, and you will get this value, and in this parameter R per unit will be equal to 0.015 and X per unit will be equal to 1.5 J 1.5 per unit. And when we have to select omega base as 1.0, so omega per unit will be equal to 314.15 at 50 cycles per second, and L per unit will be equal to X over omega, it is equal to 0.00477 per unit. And voltage per unit will be equal to its actual value divided by base value as 0.9, and current per unit will be equal to 0.01 per unit, so its actual value is divided by the base values. So this is the first step when we have gone through the calculation using the primary parameters. When we use the secondary kVA and kilovolt as base, so in this case kVA base is equal to 10,000 kVA. kVA base is equal to 10 into Ns over Np, it is equal to 1.0 kilovolt. Sorry, this is not kVA, it should be written as kV. Kilovolt base should be equal to 10 times Ns over Np, and it is equal to 1 kilovolt. Then the base current will be equal to kVA over kilovolt, it is equal to 10,000 ampere, and Z base will be equal to voltage square times 1000 multiplied by 1000 divided by kVA, it will be equal to 0.1 ohms. You can go through this calculation, as I'm going a bit quicker. You just have to solve all these calculations by your hand to understand the concept. So you just do not have to listen to it or just read it, you have to solve it on your own. So get the basic understanding of this calculation. You just have to use the same formulas to get the actual values. Once you get the actual values, the base values and actual values, then you just have to divide the actual value with the base value to get their per unit value. So once we get the base values of current, voltage, power and impedance, then we are going to refer it to the secondary side. Then Z primary referred to secondary will be equal to this formula. Using this formula you will get the value of ZPRS, and Vs is equal to 900 volts, which is equal to 0.9 kilovolt secondary voltage. So secondary current is basically equal to 100 amperes. So now their per unit values will be their just actual values divided by the base values will give the value of impedance per unit, which gives the resistance and reactance per unit. And for the inductance we have L per unit is equal to 0.00477, as we solved for the case 1. In the first case it will remain unchanged, and voltage per unit is equal to again 0.9, and current per unit will again be 0.01, which was the answers we obtained using the first case. So what we concluded by this example, that in this transformer, when once the voltage bases in the two circuits are chosen according to their turns ratio, then the per unit values of all the parameters remain numerically unchanged, whichever side of the transformer they are referred to. Whether you refer the circuit to primary side or you refer the circuit to secondary side, practically there is no change in their per unit values. Logically you can see, if you do not go to the per unit calculation, their actual values are quite different. But in per unit system there is no change in their values, whether you refer it to primary side or you refer it to the secondary side. This is a very big advantage of using the per unit system in case of transformers. So in practical term, basically it means that in per unit system of calculations, the turn ratio problem is taken care of once and for all by selecting appropriate voltage bases in the primary and secondary circuits. So this is the main concept of per unit system when we apply it to the transformer. In the similar fashion, when we'll solve the power system in the next lectures, you can simply apply this per unit system to any kind of equipment in the power system, whether you solve this system for the transmission line, whether you solve it for the generation side or the transformers or the any equipment that we use. this system is applicable to the whole power system, and it has a lot of advantages as compared to the actual system of calculations. So just do practice these numericals, and I will put some more examples for your understanding in the class session. And I hope after listening to this lecture, if you feel any difficulty, we will have the discussion in our online session. Till then, Allah Hafiz.